Welcome to the latest edition of SAE Media Group's Expert Insight series presented by Renishaw. My name is Woodrow Bellamy. I'm the Aerospace and Defense Editor for SAE. And on this edition of Expert Insight, we'll be discussing metrology-led automated manufacturing with traceability by design. Today, we are joined by Dan Skulan. He is a leader in aerospace and defense manufacturing who specializes in precision metrology, additive manufacturing, advanced automation, and smart manufacturing principles. He brings deep expertise in Industry 4.0, digitization, adaptive machining, and modern inspection strategies. And he will be answering some questions about automated manufacturing during our interview, which we will begin now. So, Dan, as you know, aerospace and defense manufacturing is evolving quickly. From your perspective, what's driving the biggest changes in how parts are made today?
Well, first of all, we have to be competitive, and that's driving a lot of the innovation in aerospace and in defense areas in both cases. So, when we're being competitive, we have to come out with better and better technologies. Those technologies are requiring higher amounts of precision, higher amounts of automation in order to make sure that we can repeatably make these products. And that's on the backdrop of having a huge number of people retiring out of the industry. So it's not uncommon for me to go into shops and have 20, 30, 40% of the staff either retiring or planning on retiring within 5 years. So if you couple those two together, a need to be competitive, to come out with new technologies, a need for these technologies to be highly precision and automating so you can get the production out the door. You couple that with the fact that you don't have people with a long experience of skill, you're bringing in a lot of new people. That's a lot of challenge that the industry faces right now.
So, Dan, many manufacturers are trying to increase productivity without sacrificing quality. How do you think companies should approach that balance?
Well, there's several things. What's being done in the industry now is using things such as digital twin. And digital twin allows you to investigate different methodologies prior to physically doing the machining and process. So it's a really interesting way for people to develop new ways to produce parts and verify a process before actually going through the cost of tooling up machines. However, the digital twin philosophy does require that you have tangible reference. So a model can be a perfect machine, it can be a perfect part. You can tweak a model if you want, but at the end of the day, you're not selling models. You're not selling digital information about a part. You're actually selling, creating, building a mechanical system out of that part. So when you're doing this, it's really important that you have metrology in the process. So using digital twins is a great start. Then in structuring your process, you need to understand, you need to have a stable manufacturing environment, understanding and measuring, compensating, and certifying the positioning capability of the machinery that you're using to produce parts provides that stability, that reference that you can go back to when you're using digital twin and ultimately even use an artificial intelligence. Both of those tools require that you have tangible evidence and stability in your manufacturing process that you can use when you're testing out these different methodologies. That allows you to build quality into a process while you're doing your machining and whatever type of metal forming that you're doing.
And speaking of machines, we hear a lot about automation becoming more accessible. What does it take for automation, including robotics, to be truly useful in precision environments?
Well, first of all, if you think about it, CNC machining is automation. Back in the day, early on, there's a lot of manual operations now. CNC machines are under computerized numerical control, and that is automation. But the use of robots, which is even higher level of automation, moving parts through factories, and even using robots now for some basic machining, the use of robots is increased exponentially over the last decade. In fact, the amount of robots that are supplied in the last year was about 600,000 globally versus 200,000 CNC machines, so almost 3 to 1. But when using robots, very similar process. You need to make sure you have stability. So incorporating robots, incorporating into a process, you need to make sure that that equipment is zeroed out, that it's certified and that can move correctly. So you can use offline programming tools to program the robot to be able to move your parts or even machine your parts in space. But when you produce that program and you place it in the robot controller and the robot is told to move, it's really important that you know the accuracy of that robot is there, that the robot repeats and that it moves with a with precision and a great deal of confidence. That's the way you can incorporate automation. The other thing is automation was traditionally used for high volume parts. Now, especially in aerospace and defense, you're not doing a lot of high volume. It's a lot of changeover, short runs. So having a robot with its own sensing capability so that it can determine where the part is in space, the orientation of the part, it can determine where it's moving the part to in advance. So using probing technology, for example, on a robot allows that robot to run lights out and allows that robot to pick up and find where it is in space, where a part is in space, and move it accordingly. So these are techniques that can be used and are being used right now to automate manufacturing.
And parts in aerospace and defense can be extremely complex or made from difficult materials. How are manufacturers adapting machining strategies to deal with that complexity?
Okay, so you're absolutely right. The parts that are being made now, especially 3D printed parts, have a high degree of complexity. Interesting, high temperature, high strength alloys are used, and they're very, very expensive. So, first of all, the value proposition and what's going on in the industry is that we really can't afford to be scrapping these parts or even reworking these parts. In many cases, they have very thin walls that pressure from tooling can distort the part. So what's being used more and more is adaptive type manufacturing, where each part is uniquely measured during the process and the tool path is updated using that data. So now we can have unique parts coming out of a process, but made in high volume production or multiple part production, and make sure that each part is correct. So we introduce the part to the machine, we measure using scanning technology, we collect that data, we compare it to the original intended file, and then we update our tool path so that we follow the contour of the exact part and create features on that part. So every part can actually be unique, but dialed in and manufactured to be highly precision using on-machine scanning technology.
And final question for you, Dan. Traditionally, many shops sorry, traditionally many shops inspect parts at the end of the manufacturing process. Is that still effective today?
It's a really interesting question, and Renishaw as a company manufactures a high percentage of the CMM probes that are used in the world. They make their own CMM now, but we call that tailgate inspection. So when you're inspecting a part at the end of the line, it's very valuable information and you can get comprehensive information about the part, but it's actually a terrible way to control a process. It should be used to validate that a process is good. It should be used to examine different tooling methodologies, different cutting methodologies, different materials, different machines. However, when you're trying to run a process, you want to build quality into the system. This provides not only a check in making sure that every stage in the manufacturing process is checked so that you can pull a part out. If a part is scrap in op 10, there's no reason to go all the way through to op 120. So you measure it at op 10. And ideally, what you do is you measure it before the part is cut. Then you cut to tolerance, validate it again before it moves on to the next stage. This does a couple things. It preserves the value of these parts. Again, a lot of these parts are extremely high value before they're even starting to do any machining on it. But it also captures valuable traceability data. And that traceability information is becoming more and more required. Department of Defense, Department of Energy, civilian aircraft. We want to have traceability, not only of the final part measurements, but what was done to that part from the initial material through all the stages of manufacturing to the end. So building quality into the process is the way for people to be competitively making parts, producing parts in volume, and it also provides the ability to trace along with producing quality parts.
Well, thanks for answering those questions about automated manufacturing, Dan, and I'm sure you gave our audience a lot to think about there. That brings us to the end of this edition of our Expert Insight series presented by Renishaw. For more information about Renishaw, go to www.renishaw.com. And thanks for watching this edition of Expert Insight.